Circuit switching. What we have is device A, we have device B. For device A to communicate with device B, what happens is a circuit is created at the start of the comms, of communication. So let's imagine right now that device A is a credit card reader. Customer goes into a shop, they put in their credit card or their debit card, they type in their PIN number. This is a server for a bank. The cashier types or clicks on send. A circuit is created between these two different devices, between the sender and the receiver. The data is passed along this circuit. So I'm sending the transaction information like $4.99. This keeps occurring until the end of comms. So once the end of the communication, the link is gone between the sender and receiver. The circuit links that makeup circuit are removed. This circuit, we can call it a dedicated circuit. So I'm going to use the word dedicated circuit. This means that no other person can use this circuit whilst it's being used between device A and B. Once they've finished, and let's say this device wants to send something, they'll set their own circuit like that, and no one else could be using this circuit during communication. So where would you use circuit switching? Well, I've given you one example to start off with, which is like a card reader to a bank server. You've got things such as traditional telephones, so old school telephones. You would also have emergency services, communication, air traffic control, military, live broadcast feeds for TV, video conferencing, which is a big one. This is like ding ding ding, top answer. You would have point of sale. So this is kind of like a point of sale system with a card, but when you go to a supermarket and you pay. So all of these are examples of where circuit switching would be used. And the benefits of doing this are the following. Number one, the dedicated channel. Dedicated channel basically is allowing just you and the other person to communicate, which means you can take advantage of all bandwidth. It's all yours. So all the bandwidth belongs to you. It allows you to have two-way, real time, so simultaneous conversations. So it allows device A and B to talk to each other both ways at the same time without any lag, any delay. So no delay. And there's no delay also because there's no packet switching. It just goes along one channel. So it just follows the path. We'll look at packet switching in a minute, where it may bounce around different paths, not always the shortest path, to get to the final result, the final destination. And finally, the data arrives in order of its sent. So the packet switching, which we'll look at, it has to put packets back into order when it arrives, which takes a bit of time. Circuit switching, it arrives in the order which is sent, so the other end doesn't have to reassemble it into that order, which means it's going to seem to be quicker. There are negatives, like data can be corrupted, but that's the same with packet switching as well. Data can be corrupted on its journey. Data is less likely to get lost. Well, packet switching and circuit switching is going to be the same in that respect. Data won't really get lost in either of them. It's very rare. And as I said previously, all the data is sent along the same route with circuit switching. All data, same route. Okay, so when we look at packet switching, it works slightly different, actually quite a bit different. The first thing is a circuit does not have to be established, so no circuit established. What does happen is, let's imagine that we are wanting to send an email. This is our email data. That email data is split into packets. That's our first thing. So data is split into packets. It's then sent at packets, and those packets take different routes. They go from node to node, or router to router on their journey, where the packets are examined. So we check the IP address of the packet, the destination IP address. Where does it need to go? Okay, cool. And then it eventually passes it to its final destination. The packets are reassembled into correct order at the final destination. But it has to wait until the final packet arrives first. The bandwidth, or the paths, are shared, so it is shared bandwidth, unlike circuit switching. Data does arrive out of order. Data can also be corrupted, like in circuit switching, so it could be corrupted on its journey, but it's not likely to get lost. Not likely lost. This is a packet. A packet can be split up into 3 different parts. You've got the header, a payload, and what's called a trailer. The header is meta information. It's basic information which is going to be needed to help direct the packet to where it needs to go, such as the sender's IP address, the receiver's IP address, so that data can be sent back, what protocol is being used, but also the current packet number. So if you've got like 1,000 packets, this would be like packet number 1. That allows it to be reassembled with ease. So we call that a packet number or packet sequence number. I'm just going to put sequence, and that is in the header. The payload is the actual data being sent. So it'll be like, give me Netflix, or I want this movie. That'll be in the payload. The trailer has error correction, so it'll be using like a checksum to make sure that in terms of the accuracy of data is high, as well as data to show that's the end of the packet, to basically be saying this is the end of this packet. Expect potentially another packet after me. And there'll be another packet sent after that with the same data sheets at the end. It would also have in the trailer the total amount of packets which are being sent, so like 1,000. So in the header it will have like 1 out of, in the trailer, 1,000. So that way the receiving computer knows how many packets it is to be expecting as well. So header, sender's IP address, receiver's IP address, protocol being used, and the packet sequence number, like packet 5 out of, and then in the trailer it will have the error correction method, which is like the checksum, which is important you realize that, recognize that, state that, as well as data to show the end of the packet, such as the total amount of packets also which are being sent, like 1,000. Payload is the data. So an important device in this whole situation is the router. Why do we need routers though? So I'm going to have a quick overview on why we need routers. Well, not only can routers act as a firewall, not only can they act as a gateway to the internet, but they also allow for LAN and internet to communicate, especially as we're using different protocols. So these are like your go-tos to begin with, and this is not to do with packet switching yet. So routers could be a firewall, they act as a gateway, they allow different protocols to be used between the local area network and the internet. But also, now we can get into packet switching. Routers forward packets on between different networks. So this could be a network, this could be a network, this could be a network. So routers forward packets on between networks. Every router has a public IP address. So it could be, so that data could be sent to it. And the router itself holds basically a list of local addresses. These local addresses are basically the private IP addresses of devices on a network. So let's take a classroom. So give me a second, I'll mock this up. We've got a classroom, we've got a router for the classroom, we've got computer, computer, computer. Each one has their own private IP address. That means that no one on the outside will be able to communicate with them. This computer wants to go on the internet, so we send a request to their router. The router then will be able to translate this private address into the router's public IP address. So that, let's say Netflix, we want some movies. Netflix will see the router's public address. Oops. And send it back to the router. The router will then translate this back into the private address and send it to the correct device. Or it helps it send it to the correct device, shall I say. So that is why we need a router. We need a router for all of these different reasons. To act as a firewall, to act as a gateway, for it to be able to communicate or allow communication between the local area network and the internet, to adjust to different protocols, so that it forwards packets between different networks, so that it stores a list of private IP addresses, local addresses, and excuse me, translates it to the router's public IP address, so that it gives it internet access. So now finally, what's the role of a router in packet switching? Or another way of saying it is how a packet is sent over the internet from a router to a server. Well, we know that each packet has an IP address of the destination. So we've got our packet in the header, got IP address of destination. D is destination. Each router has what's called a routing table. It contains a list basically of different potential pathways which could be taken. So you've got a routing table, and it's got basically IP addresses of routers on pathways, on different paths, and it will make a selection for router on the best router to use next, and we call that the next hop. So this router might look this way and see that there's too much traffic, so we'll use its routing table, find a different router. Okay, that one's the next best bet. It's a bit longer, but that'll be our next hop. So after we check the routing table, routers, forward packets to destination, and because of this and the routing table and the different potential ways we can move forward, routers mean that packets may take different routes to destination. And then finally, at destination, packets are reassembled. Keep in mind that these routes are normally, we go for the most shortest route, but it could also be available route due to traffic or bandwidth available. Okay, so pause the video, give this question a go yourself first. Okay, why would we use circuit switching instead of packet switching for video across a network for video conferencing? Well, in circuit switching, we have a dedicated circuit. Within this, we have whole bandwidth. This means that data will travel faster. Not only will they travel faster, the packets arrive in order. They are sent, which means no transmission delays. So suited for real-time application. Appreciate it, it's more expensive to do circuit switching. So these are all the reasons why we would use circuit switching. I would then mention in my answer about packet switching against each one. So shared instead of dedicated, and that means shared bandwidth. Which means that data travels slower because of this, which means packets arrive out of order, so need to reassemble. There is a slightly higher chance that packets could get lost as well. Both these factors means that actually you can have a transmission delay. Pause the video, give this question okay yourself first. Okay, so this is slightly different because we're talking about saying an email. Why would we use packet switching? Email doesn't need real-time synchronous communication. The message, and say an email message, is only read when all packets received. Delays in packets or delays in transmission doesn't matter much. It doesn't matter much if it takes a bit of time for an email to go through. Unlike video. Therefore, sending data on different routes shared bandwidth packets arriving out of order is not an issue. Remember, packet switching is going to be cheaper than circuit switching. So therefore, no need for dedicated, continuous circuit. So its email is asynchronous. Its methods. It doesn't rely on it to be in real time.